welcome to this lecture on hardware security. So, we shall be continuing our discussions on elliptic curve cryptography. In particular, today we shall be trying to understand about how to parallelize the Montgomerie ladder that we were discussing. So, we will be discussing about some potential opportunities of parallelization. We shall be following with the detailed description about how to design an elliptic curve processor. So, we shall be looking into the overall architecture of an ECC processor. We shall be trying to get into the various components of the architecture like the register bank, the ALU, how the control unit would be designed, and finally, the inversion when we convert back from the projective coordinates back to the affine coordinates. So, in particular, I will be not talking about a design based on the Montgomerie trick that we have seen, but rather this implementation will be on the plain like double and add algorithm, that is the initial naive double and add algorithm. But using this idea, you can easily extend it to to other variants of the elliptic curve processor. So let us start in that case. So, this is the ECC hierarchy that we were discussing. So, as we discussed that there are different levels of the elliptic curve operations. So, the overall objective or overall what we try to do is we basically try to have efficient implementations of point multiplication or scalar multiplication. And therefore, right, if we can when we are going into hardware design, right, we always look for opportunities of parallelism. So, that is the inherent or one of the important selling points of hardware design over software. So, therefore, right, we would like to of course parallelize, but whether we can parallelize is always constrained by the amount of resource that we have at hand. Okay. So, therefore, right, let us look into or have a quick look into the Montgomerie structure, where we essentially had a point doubling and a point addition. So, these are the point doubling and the point addition equations actually. Okay. So, now if you observe that I have tried to give potential parallel strategies for scalar point multiplication depending upon the fact or assumption that suppose we have got one multiplier or two multiplier resource at hand, okay, because multipliers are typically quite consuming in terms of resources. So, therefore, right, if we say for example, that our architecture can support one multiplier, then we easily see that the point doubling operation essentially will require you can essentially perform them in this in the cycle. For example, you can essentially implement them using so these are the equations. So, therefore, this is the multiplier, for example, where you are computing Z2 which is equal to T into Z1 square. So, there you are basically expanding this multiplier. Okay. Likewise, right, if you see the point addition equation, in the point addition you see that I have got two multiplications, like for T1 I have got one multiplication and for T2 I have got one multiplication. Okay. Likewise, for cycle 1A there is no multiplication, okay, but for cycle 2 I have got again one multiplication required. So, therefore, right, the whole idea is that depending upon we again assume that the squarings and the multiplications with constants can be performed without any multiplications or without any explicit multipliers. Okay. So, therefore, right, with these equations in mind, okay, and with this kind of computations required for doubling and addition, let us try to see that how we can parallelize the Montgomerie algorithm. Okay. So, in Montgomerie algorithm, if you remember, this was your scalar k, and then you essentially initialized x1 and z1 because you do not operate on y coordinates here. So, you have got, and you are doing on projective coordinates. So, you need the x and z coordinates, and for x2 it is a doubled result. So, therefore, these are the corresponding doubled equations. So, if ki is equal to 1, you basically run an iterative algorithm from L minus 2 down to 0. So, this is the MSB first algorithm. You basically add in x1 z1 and x2 z2 if the ki is 1, and you double x2 z2, and if ki is equal to 0, then you do the opposite. That means, you add x2 z2 with x1 z1, but you double x1 z1. Okay. And finally, the result is x1 y1 x2 y2, but from using that you finally want to return the result back to affine coordinates. So, you make a transformation from the projective coordinates back to the affine coordinates. So, therefore, right, what we have written as a part of step 5, there are the steps are 5a and 5b. So, either you are doing 5a or you are doing 5b operations. Okay. So, therefore, now what we are trying to do is we are trying to parallelize this point multiplication operation, and let us see how or what we can do. So, therefore, right, so these are the two corresponding strategies that we mentioned. Suppose if we allocate one multiplier, okay, to each of the m add and m double. That means, suppose you have got two multipliers and you allocate one multiplier each to m add and m double. Okay. Then you can parallelize steps 5a and 5b, because now you can like do this addition operation and double operation in parallel, because you have attributed one multiplier to the to addition and one multiplier to the doubling operation. Okay. So therefore, right, if you do that, then you see that 4 clock cycles are required for each iteration. Okay. So therefore, right, I mean, so that means, right, the total time which is required is nearly 4L. I mean, is nearly 4L. So therefore, right, I mean, this is the amount of time that your algorithm will take. Okay. On the other end, if you can parallelize the underlying m add and m double, then we cannot parallelize level 1. Okay. So thus, if we have a constant of two multipliers. Okay. So we have a sequential step 5a and 5b. So now the total time will be 3L actually. Okay. So therefore, right, I mean, you see that depending upon what parallel strategies you have, you essentially, I mean, like you have got two alternatives. Okay. But on the other hand, if you can parallelize both the levels, that means level 1 and level 2, then you can actually reduce this time to 2L clock cycles. Okay. You can reduce it to 2L clock cycles, but this will require 3 multipliers now. Okay. So you see that the more resources you can expend, you can actually parallelize the Montgomery ladder quite significantly. Okay. And that's why, right, we conclude that the Montgomery algorithm is highly parallelizable. Okay. And it is helpful in high performance designs, and also, right, for low power and high throughput, both kind of like applications, because on one hand, right, you essentially can have probably resource constrained environments where you essentially can still perform Montgomery ladder reasonably well, even with say 1 multiplier cost. Okay. On the other hand, you can also go for quite high throughput designs actually. Okay. So therefore, all depends upon how much resource you have, but the point is, right, that the Montgomery algorithm has scopes of parallelism, and therefore you can try to capitalize on that. Okay. So now with this background, we are essentially like let's look into a possible case study where we would like to design ECC processor, and these are the corresponding parameters of this design. So this design is on GF 2 power of 233, which is essentially one of the fifth standards, okay, of our elliptic curves in characteristic 2 fields. So the curve is a random curve of this equation, y square plus xy equal to x cube plus ax square plus b, where a is equal to 1. Okay. But you can see that according to the fifth standard, which you can also look into the NIST corresponding website, okay, you will see that the base points like the p, for example, that we were talking about, essentially are 233-bit constants. Okay. So here are just an example just to show you how it looks like. So you see it's pretty like big number. So you basically have to do arithmetic and computations with such kind of supporting such kind of large arguments. Okay. So the constant b for the curve is again like given in fifth standard, and this is essentially shown here. Okay. These are just for the sake of completeness, trying to give us an idea about how the constants look like. Okay. So now we would like to essentially develop this elliptic curve design. Again, this is our hierarchy. We want to implement the scalar multiplication, but we have to start from the bottom, because you have to implement all of this multiplication and like the field operations, and then the doubling and addition operation, and finally the scalar multiplication, right. So this is the elliptic curve hierarchy. Okay. And if you look into the code hierarchy, so we will be trying to give you some indications about potentially how we can write for example an RTL code. So I will be using Verilog, but you can easily generalize it to other RTL languages. Okay. So a little bit of background on Verilog would be handy here. Okay. And though not in much details. So for example, like for the field operation, as you can see that the basic blocks are multiplier, squarer, and a quad block. Okay. So if you remember in one of our previous lectures, right, we have been discussing about how to realize these architectures, where we had looked into the Karatsuba multiplier, where we have seen the squarer architecture, like how we can do squaring in characteristic 2 fields, and also how we can do quadding and what are the advantages of doing that in FPGA topologies. Okay. So now we would like to build upon a top architecture using these components, and finally, right, the computations will be done or accumulated or done in an arithmetic logic unit. So this is the elliptic curve logic unit or ALU, and there is a corresponding register bank which essentially is kind of stores temporary data, also takes initial data like the constants are loaded into the register bank, and all the computations are done kind of so it's like a scratch pad where you are basically doing your computations and kind of storing the temporary result. And finally, all of these are kind of combined into a scalar multiplication. This is your top level module or ECS mul, where you are basically essentially like taking the input, that is the corresponding like key, and based upon that you are doing your scalar multiplication. And finally, when the result is done, then you essentially get a done signal to flag that the result of the computation is complete. Okay. So now let us look into the processor overview. So here are the 4 important components of my design. So I have got, as I said, the register bank and the arithmetic unit, which are kind of handshaking with each other. The register bank is essentially storing temporary data. Okay. And the ROM essentially stores the curve constant and the base point. So this stores the px, py, and also the base point. Okay, this is a base point and also the curve constant. So a is equal to 1 in this curve, but b essentially has a non-trivial value which is stored in the ROM. Okay, so this data essentially is sometimes passed to the register bank. Okay, or the register bank also takes data from the arithmetic unit. That means the arithmetic unit performs some computations and then stores the result back to the register bank. Okay. Now the register bank and the arithmetic unit also does handshaking with each other. So that means like when the arithmetic unit requires some data, okay, it essentially looks into the register bank, that is the scratch pad, and from there it gets temporary results to do further computations. But then the entire like ringleader sort of, or the controller is the control unit, which basically essentially performs the or rather sequences the field operation. Okay, like the whatever operations will be performed and the sequences in which they will be performed. So that decision is done or made by the controller or the control unit. Okay. So roughly speaking, as I said previously also, it is very important to understand the data path and the control path of your design. So this control unit is your control path, whereas this essentially comprises of your data path of the circuit. Okay. So we essentially have written like individual Verilog codes for all of them. For example, the register bank is being written as regbank.v, okay, and the arithmetic unit as ec_alu.v, and the controller using another Verilog file. Okay, so all of them have been built in a modular fashion. So now let us look into the register bank. Okay, so in the register bank, which is in the heart of like the design, so essentially there are basically like 8 registers, each of size 233 bits, because my arguments are of size 233 bits. They are organized as 3 banks, okay, and they are implemented as dual port distributed RAMs, which are present in the Xilinx FPGAs. Okay, but pretty much you can find similar constructs in other architecture or other platforms as well. Okay, so the main characteristic of this memory bank is that for example, if you look into this architecture and you see the RA1, which is essentially one of the banks, you see that there is a corresponding address, okay, and you essentially can perform and like asynchronous write. I mean, you can perform an asynchronous read and a synchronous write. That means with the clock you can essentially set or enable like the write signal here, which is the WE signal, and you can actually like flag a corresponding address and you can write into that address synchronously with the clock. Okay, but you can also read. So you can essentially read at any time. That means the read is always enabled, but from where you want to read, for that there is another address. Okay, so you essentially have got an address 2. So you will see that there is an address 1 typically which is for writing, and address 2 which you are using for reading. Okay, so these are essentially because you essentially, so these are dual port RAM, so you can like write into a different location and you can read from a different location. So that essential provision is provided here. Okay, so you can observe that you can essentially read 2 data, but you can write into 1. Okay, 1 address. So likewise, right, you will see that in the register bank there are like 3 important registers, RA1, RA2 and RC1, okay, or rather RA, I would say rather RA, RB and RC. The reason why we have got 3 register banks is because we are doing our computation in projective coordinates. So we have got x, y and z. Okay, so RA is essentially used for processing the x components, whereas this is for the y components and this is used for the z components. Okay, So, if you read this table, you will see that we kind of detail about the functionalities of each of these registers in a very high level, So, for example, array 1 is used during initialization. It is loaded with px, okay, that is the x coordinate of the base point. It stores the x coordinate of the result, okay, that is the intermediate results when you are doing your computation. It is also used for temporary storage. Okay. Array 2 is used for storing px. Okay. RB1 is used for during initialization it is loaded with py, and it also stores the y coordinate of the result and is also used for temporary storage. RB2 is used for storing py. RB3 is also another register which we use for temporary storage, and RB4 stores the curve constant, which is small b. Okay, so you take from the RAM and you store it in RB4 for like faster access. And RC1 essentially stores the z coordinates. So, you remember, like we initialize the z coordinate with 1. So, you basically initialize it and you set it to 1, okay, and you store the z coordinate of the projective result, okay, and you also store and it is also used for temporary storage. Okay, so RC2 is again another temporary register which we essentially use in our architecture. Okay, so another point which we will see later on is that this computation takes place in mixed coordinate. That means like one of the coordinates is in projective domain and the other one is in affine domain. Okay. So with this background, we are more or less we have understood how or what are the functionalities of each of these registers. You see that there are some output ports and input ports. For example, the output ports are A0, A1, A2, A3 and also Q in. Okay. So these are buses, okay, that means these are wide n bit data which is being passed. So this data passes from the register bank and goes to the arithmetic logic unit or the ALU, okay. And there are some inputs like C0, C1 and Q out. So these inputs are the outputs of the arithmetic logic unit, okay. So they are essentially taken from the arithmetic logic unit and fed back into my register file, okay. So this is a potential Verilog design, okay, of the register bank, okay, and if you can see that this is the module of the register bank. In particular, I would like to highlight few things. For example, I would like to highlight the hierarchy here, so you can see and easily understand this part. That is, there is a clock, of course, because there is a synchronous event which is taking place. As I said, that the write is synchronous. There is a like part of the control word which is used. So the control word is essentially divided into two parts. One is the lower part and the one is the higher part. So the higher part is indicated as CWH. Okay. There are inputs like C0 and C1 which are essentially inputs which are received, okay, and there are outputs like A0, A1, A2 and A3. Okay. Another important point which may be observed is that how we have instantiated the distributed memory. So these are like the three components of register bank, RA, RB and RC. So therefore we have got three instantiations of the register bank. Okay. Again, this is a particular instantiation which was done on a Vertex 4 kind of environment. For a different platform we have to look into what exactly the module description should be. Okay. So there are three register banks, register bank 1, register bank 2 and register bank 3. All of them have got a D in, which is the data input which it gets in. There are two addresses, address 1 and address 2. As I mentioned, address 1 is used for writing and address 2 is used for reading. There is a write enable because the writing cannot be done always, it has to be synchronous with the clock, but the reading can be done always. Okay, and there are two read ports like D out 1 and D out 2 for each of these register banks. Okay. So therefore, right, I mean with this background, right, you can see that there are of course more descriptions depending upon I mean essentially it is nothing but descriptions about based upon the architecture. So if you see this architecture, so based upon that these are like corresponding Verilog codes which has been written to describe the hardware essentially of the register bank. Okay. For example, like you can see that like how this A0 to A3 are fed to the ALU, so that you can see that there are essentially these are nothing but multiplexers, and the multiplexers has been written using an assign statement in Verilog. Okay. So these are the descriptions of these multiplexers. Okay. So likewise you can essentially realize the entire register bank unit, and the other important component is the arithmetic logic unit for the elliptic curve processor. So in the arithmetic logic unit there are two important blocks. One is the hybrid Karatsuba multiplier, but the inverse is not a monolithic block, but rather has been implemented using the quad block and the multiplier. So, if you remember, like we are different stages of the Itosuji inversion algorithm. So, we try to implement the Itosuji inversion algorithm, which uses the quad block as a fundamental block and along with the multiplier. The multiplication has been used at every step of the inversion routine. Okay. Now, along with these two things, right, there are some other peripherals which has been used, which are essentially quite efficient in terms of hardware. For example, the squarer routines and also the XORs, for example, which are kind of essentially done. The XOR is used for doing additions of the arguments. Okay. Now, why these kind of units are like A0, A0 square and so on will be probably understood as we progress. Okay. But this is kind of just to give an idea about how the arithmetic logic unit looks like. So, let us now try to understand what the arithmetic logic unit performs. Okay. So, the arithmetic logic unit performs point operations like doubling and addition in Lopez-Dahab projective coordinates, in particular mixed projective coordinates, and there is a final inversion from the projective coordinates to the affine coordinates. So, there are two phases of the arithmetic unit. Okay. The arithmetic unit has got 5 inputs. So, these are denoted. So, these are the outputs of the register bank, and 3 outputs which are in turn the inputs of the register bank. Now, the computation of the arithmetic unit has got 2 phases, point addition and doubling, and the final inversion. And as I mentioned, that the arithmetic unit consists of the hybrid Karatsuba multiplier, which is used at all time steps. Now, this is an important part that we kind of try to adhere in our scheduling. Since the multiplier is very kind of costly, we do not want to keep the multiplier idle at any clock cycle. So, basically every clock cycle there is one multiplication which is mandatorily performed. This is just to save the number of clock cycles. Okay. Likewise, there is also a quad block which is used in phase 2 for the final inversion, when you want to convert back from the projective coordinates to the affine coordinates. And the quad block, if you remember, like that the design that we showed, essentially had 14 cascaded steps. So, each of these steps were like power 4 circuits, that means which it takes an argument and raises to the power of 4. Okay, and it computes the coding repeatedly depending upon a particular controller or select line, and the select line essentially has got bits from 26, 27, 28, 29. So, that means you have got virtually 4 bits to implement that. So, depending upon what value you set here, what you compute is any input that you give to this quad block, it is raised to the power of 4 to the power of select actually. So, that means if alpha is my input to the quad block, and select is the value of the select line, then what I compute or get as a result is alpha to the power of 4 to the power of select. Okay. So, therefore, you basically kind of raise it accordingly. Okay. So, this is again like a very long description for the arithmetic logic unit, nothing much to see except that you see that essentially the entire design has been done in a structural way. So, we basically kind of like realize the squarer, multiplications, and separate the separate Verilog codes and just instantiate in our design. Okay. So, likewise the entire description has been given for the arithmetic logic unit. So, now you have got a controller, okay, and the controller is essentially a hardwired unit. Okay, that means it is essentially you can essentially change the control unit values as well. Okay. So, it generates 33 control signals, okay, and you can kind of reprogram the control unit to for other kind of operations as well. So, it is kind of programmable, and so the objective of these control signals is basically try to kind of determine the flow of data. Okay. For example, like C0 to C9, this is like one part of the controller, it controls the input to the multiplier and the output C0 and C1 of the arithmetic unit. Okay. So, essentially it controls the input to your multiplier, that is a hybrid Karatsuba multiplier, and the output C0 and C1 of the control unit. And there, as I said, the C26 to C29 is the select line of the multiplexers, which is used as an input to the quad block. Okay. The remaining control lines, that means out of the 33 control lines, the remaining control lines, they are used for read and write of the registers in the register file. Okay, that means they are used to control which register you want to read, write, and from where you want to read. Okay. So let's now look into in order to understand the arithmetic unit better, let us try to look into the corresponding computations. Okay. For example, let us try to look into the projective point arithmetic unit. Okay. So here these are my computations. So if you remember, like we essentially described about how to perform point doubling, okay, and we also saw how we can convert the point doubling into projective domain, okay. So so you can see, so I leave it to as an exercise to kind of check for doubling, which is relatively easy, and you know, like these are the corresponding computations which we perform, okay. So now what we would like to do, as I said, is we have to schedule these operations, okay. So these are the fundamental blocks which we have to schedule, okay. There is a restriction. The restriction is that you have got one multiplier at hand, okay, because if you remember in the arithmetic unit there is only one Karlsruhe multiplier, okay. So how many clock cycles would you require to implement this? So you see that there are 4 clock cycles which have been expended, and apparently you cannot do lesser than that, okay. So now we will try to understand, you know, like how or what are the time steps of performing this, okay. So this is a description of the point or projective point doubling sequence, okay. So you see that these are the 4 clock cycles which are required, and this is my corresponding computation which is being performed, okay. So if you observe carefully, you will see that this is a parallel architecture for performing the doubling or point doubling, okay. So in particular you see that, as I said, that in the arithmetic unit there are 2 output blocks, C0 and C1. So you can essentially kind of compute C0 and C1 in a parallel manner, okay. So you see that in C0 here I use the multiplier, okay. So now RA1 and RC1 essentially are inputs which are received from the register file, okay, and RA1 is nothing but you know, like your X1, okay, and RC1 is essentially is your corresponding Z1, okay. So therefore, right, when you are computing this RC1, which is your out, so therefore what happens is that if you see that the input to this arithmetic unit is A0, so A0 essentially will have RA1, okay, and therefore, right, so this will come here, this will come here as an input, and the other input is A1, okay. But what I choose in this as an input to this multiplexer is determined by this select line and by this select line, which are coming from my control unit, okay. So what I choose is this line. So basically what I do is I choose this this corresponding input, so that is my A0 square, okay. So that means I compute RA1 squared in this way, and for this multiplexer or through this multiplexer I choose this line, that is A1 square, okay. So I choose A1 square here and I choose A0 square here as inputs, okay. So now this gets passed into this multiplier, and therefore this multiplier multiplies RA1 square and RC1 square as a result, okay. In parallel, you also calculate RC1 to the power of 4. So you see that already in my circuit there are some squarings which have been provided. So therefore what I can do is I can take, for example, A1 which has got RC1 now. So this RC1 comes over here, and this is my RC1 to the power of 4, okay, because it passes through 2 squaring circuits, okay. So now this essentially is my is also like something which I also, so the C0 port is used to transfer the output of the multiplier, okay, whereas the C1 port is used to pass this corresponding result, which is A1 to the power of 4, okay. So this A1 to the power of 4 is now passed to this C1, which means you also have this data ready in the same clock cycle, okay. Likewise, if you see, right, so now you have basically computed in the first clock cycle this component, and you also have calculated this Z1 to the power of 4 in the same clock cycle, okay. In the second clock cycle, what you do is you multiply like RB3, which is your Z to the power of 4, with RB4. And what is RB4? RB4 was used to store the constant B, okay. So therefore, right, you basically get B and you multiply B with Z1 to the power of 4, okay, and here you essentially compute that corresponding result, okay. So likewise, you also need to calculate Y4, and you see that the computation of Y4 has got few multiplications, like it has got more than one multiplications which are present. So therefore, right, for this computation we require more than one clock cycles, okay. So what we do now is that we first like in one clock cycle we compute this part, which is your RC1 plus RB1 square plus RB3, okay, which essentially is computing this part. Remember, A is equal to 1 in this design, okay, and the other part or RA1, right, is nothing but is computing your RA1 to the power of 4 plus RB3. So that essentially computes your this plus, okay. This addition gets computed. So now in the final clock cycle, that is the fourth clock cycle, you basically add this component and you essentially get the corresponding result, okay. So you see that you need 4 clock cycles to do this computation, and if you understand, right, how this computation has been taking place, you also know how the control signals should be generated in time steps, and so that we can perform the doubling operation, okay. So let me stop here, and in the next class, right, we will be continuing about and see how we can perform the addition operation.